Thank you for all joining us. I'll start with an acknowledgement of country. So Farmers for Climate Action acknowledges the traditional custodians of the land on which we are meeting, and we pay our respect to elders past and present, and we extend that respect to any Torres Strait Islander peoples who may be present today. And we recognise that we have people joining us from all around Australia. So we're really delighted to have ANZBIG here with us to talk about their farmer guide and talk about the interesting and emerging world of biochar and everything that entails. So I'll hand over to Don, who will go through biochar a little bit more in depth.
Thank you. Thank you, Paul. I'll just share my screen so you can see that now. Thanks very much to the Farmers for Climate Action for co-hosting the webinar today, and we hope it's the first of an ongoing partnership to scale up biochar in Australia. And welcome to the ANZBIG and FCA members here today for this information session. This is on the Farmer's Guide for the production, use and application of biochar. That's the QR code there. It's up on our website, available to download now. I first met the authors of the guide, Dr. Paul Taylor and Professor Stephen Joseph, at a biochar workshop in Byron back in 2011. It had all started when I responded to an advert for an event called the Biochar Revolution workshop. So some of you might be familiar with Paul Taylor's first book, The Biochar Revolution. And that workshop ignited my passion for biochar. And here we are today, still collaborating after all these years. So I'd like to extend my gratitude to Paul and Stephen for their tremendous effort in creating this world-class reference guide. And since the draft review released in late March, we've had around 250 downloads from across the globe. And Paul and Stephen, I must mention, also offer a 2-day practical workshop if you'd ever like to get a group of farmers together in your region. The training is customised to meet the specific needs of the participants. A heartfelt thank you also goes to the supporters listed on the front cover of the guide, which is Metamorph Engineering, Rainbow Beta, the Regenerative Agriculture Alliance at Southern Cross Uni, Earthbank, the Department of Water and Environmental Regulation, and the Department of Primary Industries Western Australia under their Healthy Estuaries program, and as of today, Griffith University. So it's not too late to become a supporter of this guide and the upcoming biochar manual, which we'll touch on a bit later. The front cover there is Associate Professor Shala Hosseini Bar from Griffith University. I would like to now hand over to Melissa Rebick, who's the chair of ANZBIG and also works with Metamorph Engineering. So over to you, Melissa.
Thank you. Just sharing the screen. So I just wanted to cover off on why biochar very briefly before we go and hear more about it from Paul and Stephen. Firstly, biochar is a highly charged, high surface area, highly porous carbon residue. Its properties are made special by pyrolysis in an oxygen-limited environment. It has the capacity to remove 10% of Australia's greenhouse emissions just by making biochar from waste. Once we apply it to the soil, it can further reduce greenhouse emissions because the carbon increases in the soil with the addition of biochar. So we think that's in the order of up to 30%. No other substance can do so much for agriculture, and Paul and Stephen are going to cover off on the multiple benefits for agriculture when you apply biochar to the soil, or feed it through an animal for that matter. So no other substance can do this much for agriculture, climate change, and the global economy. So So last slide here is that we aim with our roadmap to help the biochar industry become $1 billion industry minimum by 2030. This is achieved because just by making biochar from 50 million metric tonnes of waste, we think there's 100 million tonnes available, 50 million available. The biochar sales alone are worth $15 billion. The carbon removal value, because we sell the carbon in the biochar on the voluntary market, is valued at a minimum of $6 billion. We've estimated just by applying biochar to 10% of agricultural land, it will increase productivity by $2 billion in value. The soil carbon increase value is $90 million minimum. The water savings value, because of the porosity of biochar and its ability to hold water, is $453 million. And the renewable energy savings, so when you actually make biochar through pyrolysis, you're also producing renewable energy, is worth $16.5 billion. These are the reasons to learn more about it. And Paul and Stephen, who we thank incredibly much for putting this information together in the Farmer's Guide, are going to cover off on this. And the little graph to the right shows you that our industry is increasing exponentially. It's more than tripled in the last 2 years. We do need your support to influence policy to increase its use in agriculture, and there's significant global policy emerging that mandates its use in certain countries because of its multiple benefits and opportunities for climate change and agricultural productivity. Thank you.
Thanks, Melissa. And we'll go to Paul Taylor, who's got a presentation as well around biochar and the Anne's Big Biochar Guide, Farmer's Guide. Thanks, Paul. You might just be on mute there, Paul.
Hey, thanks, guys. I was on mute. I'm unmuted. Can you see my screen?
Yeah, we can see your screen.
Great. So I should be able to make a slideshow of this. Okay, see that?
Yep, coming through
Great.
great on our end.
So yes, this is Paul Taylor. I'm actually particularly interested in climate because I'm a physicist. I worked next to the National Center for Atmospheric Research in the US for a long, long time, spent 50 years in the US. And back in the 70s, every week there was reports coming out on climate change and forest burning. That's what was going to happen. So it's all happening now. About 20 years ago, I began to see biochar as a very important solution to that. And Steve and I have worked on writing a manual and a guide to that for more than 10 years now. When we took it up again recently, there's so much new science that we decided to write a farmer's guide to kind of put that science there to back up what we're going to put in the manual in terms of recipes and actual procedures. So this is a step towards a manual. And today I'm just going to talk a little bit about the guide. Now, the farmer's guide has 11 chapters, and it's kind of got 3 sections. One is the principles and production of biochar. A middle section of 4 chapters is more the science behind it, the properties of biochar, the changes that occur when biochar interacts with soils, effects on crop and soils, and choosing and enhancing a biochar. And then we end with another section, which is more the practical methods of applying case studies using biochar in regenerative agriculture. So every chapter has a collection of key points that are explored in the chapter. It's rich in figures and captions. And there's several chapters of case studies. And we cite the literature and collected at the end of each chapter. I'm just going to briefly go through the chapters and cover a point or two, particularly more relevant to climate change. So But biochar is obtained from thermal decomposition of biomass in an oxygen-limited atmosphere. That's called pyrolysis. Pyrolysis of biomass produces energy, gases, oils, and the solid residue or biochar, and all of those have a range of uses. Nearly any biomass can be used to make biochar. You see the illustration over here. But it should be sourced sustainably. It should not be contaminated by toxic substances. And it should be of relatively uniform size, ideally, suitable for the kiln, and have a moisture content in the range 15 to 20%, just because that is more efficient, less emissions, makes better biochar. Now, when you make biochar, about half the carbon in the biomass is released into the atmosphere and the other half is captured. So what about that carbon that's released? Well, it goes like this. 100% of the carbon is in the biomass initially. When you start pyrolysis, you release about 50% of it and then into the atmosphere, and the rest remains stable in the biochar, maybe a little bit of decay over the years, because some of it's available to microorganisms and plants. Okay, so there's a net increase in carbon in the atmosphere. That's not good for the climate, but you've got to grow the biomass back. And when you if you make it fresh biomass, you grow it back. And as it grows back, you end up breaking even, where you've got as much back in the biomass as you emit to the sky. And eventually you get all the carbon back in the biomass, plus you have 40% locked up in the soil. Now, if the biomass grows fast enough, just in a few years, like fast growing grasses and shrubs and trees, then you break even very quickly. Or you make the biochar from waste that would otherwise decay very quickly, and the avoided emissions by avoiding that decay quickly allows you to break even and once again have 40% of your carbon left in the sky, left in the ground. So it's important that's not an important criteria for net drawdown. Use fast growing biomass or fast decomposing waste. I can't move forward right now. So it becomes important to emphasize that pyrolysis is not combustion. Combustion is a gas phase reaction requiring oxygen and giving heat. Pyrolysis requires heat, but not oxygen, to break down the biomass and evolve gases. Now, those evolving gases are oxygen poor, and along with oxygen deficient flames, protect the char from oxidation. All of that is shown. It's just visualizing a match. You ignite it, it gets hot, it gives off gases, the gases flame, and the evolving gases in the flame protect the char, and you end up with a half a stick of biochar, right? And no smoke unless you put the flame out. So it's this separation of combustion and pyrolysis that allows the simple kilns to be made to make excellent biochar with low smoke and pollution. Now, other products can come out of biochar. Some of those gases can be condensed. You end up with wood vinegar, which is another valuable product, promotes germination, crop yields, beneficial microbes, and controls harmful pests. And so overall, if you make biochar, think about optimizing the environmental benefits by using more of the carbon and energy in the biomass. So sun dry the biomass to avoid fossil fuels, capture wood vinegar as well as biochar, and if possible, use the energy in the pyrogas to offset fossil fuels, such as heating a greenhouse or drying coffee or drying your biomass. The next chapter, we look at indigenous practices, which go back thousands of years, and it's important to look at it because we can learn a lot from them. Traditional practices involve thermal treatment at low temperatures, usually less than 450 degrees, of fresh and composted biomass mixed with mineral sources like clay, soil, bones, shells, fired clay, and pottery fragments. In other words, typically it's made in the soil, like this is contemporary practice in Nepal. They dig the soil, layer it with some straw and leaf litter and leaves and some cow dung and smolder that away, and then they dig it in. And you end up with this very rich, porous material that's full of minerals and nutrients that are complexed with the carbon. In Vietnam, they actually deliberately soak their bamboo in ponds at the base of their rice paddies. Those ponds are rich with clay and nutrients from the rice fields that goes into the wood. And then they burn that and it burns more slowly and cleanly and makes a great biochar full of minerals. So it's this reaction with the minerals forming these biochar organo-mineral complexes that seems to be very effective. And we know it's effective because we can find the anthropogenic soils in Brazil and also made by Australian Aborigines. They had fire pits, ovens. They cooked their food in those, cleaned them out, ready for the next time. And so they produced these midden soils that, in contrast to the surrounding soils, are rich in carbon and in potassium and phosphorus. So we know this really, really works, and we can learn from that. Now, indigenous peoples often mix manure with their biochar, particularly when they've got nutrient-demanding crops. So they do combine biochar with other sources of nutrients. And then they typically allow 1 to 3 weeks before planting in the biochar, because this allows time for the biochar to age, for the microorganisms to adapt. And we're going to talk about that in one of the chapters. Now, chapter 3 is choosing a reactor. We have some tables to help you do that discuss the different types of reactors, whether they're heated internally, and by putting material on flame it, or by heating it in retorts where you heat it from the outside, where there's oxygen present, whether it's batch or continuous, fixed or mobile, what type of feedstock. And we have a table that shows you the outcome of whatever kiln you choose in terms of the types of feedstock can take, the emissions produced, the amount of energy produced, the ease of use, and the actual estimated costs and lifetime of the kilns. I'm just going to talk a little bit about making biochar on a farm using simple kilns. Now, the simplest kiln is the Kontiki, which has gone around the world as an effective flame cap type of kiln. You simply have a vessel. In this case, it's a cone, but it could be a cylinder or something else. It could be pit in the ground. And you put kindling in there, put it on fire, and then keep adding your feedstock to keep the flames going. You feed the flames, you end up with a flame cap over the kiln, and the flame cap is what burns the smoke, protects the char from oxidation, and of course heats it so it evolves more gases. And when all the gases are out and the yellow flames are gone, that means all your pyrolysis occurred, you've carbonized the material, there's nothing else to evolve, and that's the time to quench it and preserve the char. And you can quench it by spraying it. It's got to do a very good job of it to make sure it's out. In this case, I'm quenching it by pumping water from a vessel down here and into the bottom of the kiln, and I just completely flood the kiln. So you know it's completely out, and you could put nutrients in here and pH adjusters so that you end up with a biochar that's loaded with nutrients and the pH you want. You let that drain back in there so you can recycle it. It's full of smoke chemicals. You can use that on the farm too, or recycle it for next time. And then tip the biochar out, let it sun dry for 2 or 3 days, and then grind it. Here it's being ground in just a hammer mill that you would use to chip wood. Conversely, if you're, let me just say that that vessel can be any type of shape. It could be rectangular, it could be a pit in the ground, it could be very big. It could even be a stove. Here we have a stove with burners on top, and they're designed to burn very, very cleanly, and you end up with biochar in the stove. Or you can actually make biochar mineral complexes. What we found indigenous people doing, you can, instead of quenching it, you can cover it with clay and compost just to quench the biochar or snuff the biochar. Or you can stuff into a barrel various clays, minerals, straw, wood chips, and throw that into the top of your Kontiki or your flame cap kiln and just flame it away, and everything bakes in here, and you end up with 2 types of biochar, one made in the oxic environment of the flame cap and the other made in the anoxic environment inside a retort and a biochar mineral complex. So on the other hand, you might want a commercial kiln. There are various commercial kilns available in Australia. Some of them are quite simple. Some of them have designs available online. We can provide designs. So this is just a little collection of types of kilns available in Australia, and in this chapter we discuss the pros and cons and application of each type of kiln. Chapter 4 is about the properties of biochar. Now, there are physical properties, chemical properties, and electrical properties, and I've listed some of them here. I've emphasized some, like water holding capacity is a very important property to biochar in a drought stressed country. These physical properties impact biochar's mobility in the soil, its interaction with soil, water, minerals, and nutrients, and its suitability as an ecological niche for soil biota, but by virtue of the porous nature of the biochar. The chemical properties cover a whole gamut, but pH and liming value obviously are important. The cation-anion exchange capacities, the absorption and binding of toxics such as heavy metals and toxic organic compounds like pesticides. In fact, you need to take that into account if you're applying biochar and pesticides, because biochar will soak up some of them. And at the same time, biochar could also contain toxic items such as heavy metals and pH and dioxins. However, if you choose the biochar so it's made from materials that are not loaded with heavy metals, we find that there's not very many in there, and in fact most of them are bonded strongly to the biochar. And if you look for the plant available component of those toxic components by doing leaching studies, it's actually extremely low. It's often undetectable. It's below the 1% level, and you could probably apply biochar in agricultural relevant quantities for hundreds or thousands of years before you built up a level that was considered that reached the limits. Now, the electrical properties of biochar, like the redox potential, the ability to store electrons, the ability to exchange the electrons, the ability to buffer the redox potential in a similar way that you can buffer the pH. These are all very important as well. They all can be measured. And in fact, they are often the underpinning mechanism for the chemical properties of biochar. And just to emphasize in this little diagram here, a lot of these chemical properties come from functional groups on the surface of the biochar, which tend to be there more in lower temperature biochars and biochars made from grasses and manures that have nutrients in them. And in terms of electrical properties, the biochar then acts like a battery. It stores electrons and releases them, and thus controls the redox potential and these other chemical and electrical properties in the soil. Now, those properties that you measure for biochar in the lab or in fresh biochar aren't necessarily the same as the ones that are going to be active in the soil, because the biochar actually changes in the soil. And this diagram here illustrates how that might happen. The biochar with its pores, internal pores. In moist soil, there's an exchange of water and exchange of volatile or organic and inorganic compounds into the soil, and also from the soil into the biochar. Bacteria and fungi start entering the biochar. You start to form microagglomerates of carbon and the minerals. They form into microaggregates, and they form plaque layers on the surface in the pores. That plaque layer can crack off and expose fresh biochar, and so the process continues. So the biochar really changes in soil, and it also changes in compost and in animals, except that there it occurs even faster. So here we could see some aged biochar. You see fungi growing into it, and you see the plaque layer, and you can see all the minerals that are on the surface of the biochar. Now, the next chapter 6 is a chapter on the effects of biochar on crops and soils. And one of the first things we do is look at the biochar effects on crop yield. And in this chapter, we do this by looking at a lot of meta-analysis. So here's a meta-analysis of biochar effects on crop yield, 2 different ones. Each 50 or 60 studies involving hundreds and hundreds of trials done by separate authors in separate times. And you can see that if we look at all the biochars of all types in all climate zones, in this study, we get about a 7% increase over a range, of course, but average 7% compared to the non-fertilized control, and fertilized compared to the non-fertilized control is about 26%. In another study done 3 years later, they found about equal effect of biochar and fertilizer. So it gives you a sense of the variation in these meta-studies, but probably some of this difference is because we're learning to make better biochars and applying them more carefully. So they're working better. In both cases, though, the studies found that biochar and fertilizer combined worked better than either one separately. Now, you can break these studies down in meta-analysis because there's so many studies and look at it in terms of what the biochar is, what type of crops you apply to, what the biochar is made from and how it's made, what type of soil, what type of climate. And this is the same type of graph here turned on its side. So we see here the blue dots are relative to non-fertilized controls. So you see here that biochar works best for maize in versus unfertilized soils, which is you're growing maize in Africa or Mexico and you can't afford fertilizer, then biochar is going to help you out a lot. It worked best with feedstocks made from cereal residues. It worked best made at lower temperatures, below 400 degrees. It worked best at low rates, less than 5 tons per hectare. It's very important to get the nitrogen balance right in the biochar by mixing it, adding it to the soil or the biochar. In terms of soil properties, biochar worked best at low pH, in poor soils, in sandy soils, in low CEC soils, and low organic carbon soil. So all the bad soils is where biochar works best. And similar things, if you compare it with fertilized controls, those are the red dots, they tend to follow the same trend, but obviously biochar works much bigger yield effect in unfertilized soils. So the important thing is for maximal productivity and profitability, choose and design a biochar to meet the farm constraints and nutritional needs. And just a couple of key points, the most effective biochars for crop yield and promoting microorganisms are made from grasses, straws, poultry litter, manure, and clean biosolids at relatively low temperatures. For improving soil physical characteristics, you can add in bamboo and hardwood biochars. And in fact, perhaps the best results when you're not sure or you want to cover multiple constraints is to make thick feedstock biochars and even make them at various temperatures. In other words, mix your biochars. Create an analysis restaurant for the plants and microorganisms. Wood vinegar is becoming more and more prominent and recognized as a very valuable product on the farm. And even there are studies combining biochar and wood vinegar, meta-analysis included. This is looking at the co-application of biochar and wood vinegar on growing basil. And this is looking at the soil biomass carbon, so building up carbon in the soil from the bacteria and from the biochar, and looking at it in the bulk soil and in the rhizosphere of the basil. And you can see here that biochar plus wood vinegar work really, really well for building up soil biomass carbon. We can also look at nitrogen uptake and phosphorus uptake, and you see the biochar and biochar plus wood vinegar worked about the same, similar for the use efficiency. So the general concept here is wood vinegar can be very useful. There are many other things they measured, and a biochar plus wood vinegar can be even more useful sometimes, or at least as useful. So this is looking at biochar effects on crop production. The same chapter, but we're looking at how biochar modifies soil pH and EH. So we have a range of pH and a range of EH in soils. Soils typically lie in a range like this. And then there's the most favorable conditions. You want your pH in a kind of neutral, and you want your EH in this range for most favorable. So you start adding biochar to the soil, and we find that as we add the biochar in bigger and bigger quantities, application rates, we bring the soil into a favorable range from wherever it was. But if you add too much, you take it out of the favorable range again. So it's important to get this balanced and perhaps do trials to see what's going on. Another section in this chapter is looking at the effect of biochar and soil carbon and climate change mitigation. This is a Walling-Bar 10-year study. They added 10 tons per hectare of biochar, which is 1%, eucalyptus biochar, produces 550 degrees in the top 100 millimeters. And then they measured the carbon in the top 75 millimeters. And these are the results. So we've translated that into this diagram here. Here's the biochar addition. This is the carbon in the biochar. It was 5.7 tons per hectare of biochar carbon as opposed to biochar itself in the top 75 millimeters. And what they found at the end of 10 years was an extra 15 tons. It went from 35 to 50, extra 15 tons. So they put in 5.7 and ended up with 15. So it's an extra 9.3 tons that come from soil organic carbon building up just from adding the biochar. At the end of 8 years, in some of their trial plots, they added another 5.7 tons of biochar carbon, and the whole process started over again. So basically what we're showing is that putting the biochar in itself adds carbon to the soil, but also promotes additional soil carbon due to the buildup of microorganisms, the dying of the microorganisms in the soil and the roots and proliferation and so on. So biochar can increase the soil organic carbon saturation level. Instead of being saturated at 3 or 4%, it might saturate at 5%. And then when you add more biochar, you can increase the saturation level all over again. Okay, now biochar can also enhance soil inorganic carbon as well as the soil organic carbon. Now, if you take that and instead of applying the biochar once at year 1 and again at year 8, you just apply the biochar every year. Now, why would you apply it every year? Because it costs money to apply the biochar, and the biochar is going to produce yield benefits, as we saw, and you can get profit from that. And that profit allows you to repeat the process. And if you applied just biomass, such as compost, then it mostly decays away. And at the end of 10 years, you don't have that much built up of carbon. But if you apply biochar, it's stable, it's a little bit of decay, but it adds to itself, and you end up with a large buildup of soil carbon. But based on the previous slide, we also build up extra soil organic carbon from the biochar, shown by the red curve here. And if we went with the previous study, it's even more than the buildup of carbon. So it would be a massive buildup of carbon from the combination of the biochar carbon and the soil organic carbon. And it turns out that it's probably better to add your carbon every year incrementally into the soil, into the rhizosphere of the plant, and receive those incremental profits while you build up the long-term benefits of carbon mitigation and improving your soil structure and resistance to drought and so on. So we talked about, I hope we mentioned or we got that we want to make the biochars fit for purpose. And so this chapter 7 is about choosing and enhancing biochars to meet soil constraints. We discuss the methods. You can pre-treat the biomass before pyrolysis with clay, chemicals, minerals, and nutrients like the indigenous people did, or you can mix them together and combine them and treat the combination like indigenous people also did. You can age the biochar by passing it through some interim process before applying it to the soils. That could be feeding to animals, using in animal bedding, using in aquaculture, using in water treatment, nutrient catchment, but then cascading the biochar back into the soil and getting that plant and soil benefit as well. And all of this has been studied. There's tens of thousands of papers every year now on biochar. Here you can see the microorganisms attracted to the nutrients that are complexed into the biochar when you make an enhanced biochar mineral complex. So applying biochars, every chapter has key points and guidelines. So these are the guidelines summarized for applying biochars. You want to combine the biochar with fertilizer. You want to apply in the root zone of seedlings because it works better there. It's the only place it really works in terms of helping the plant out, and apply it every crop cycle. You want to optimize the rates because the rates for optimum disease resistance may be different than for optimum health or for optimum profitability. So you conduct trials, get the rate right, and apply the biochar. The application methods, root zone layers, bands, and topsoil injection are really good because you get the biochar where it's needed, where the microorganisms and the roots are. And there's tools to do that. You can apply the biochar as a liquid biochar, or you can apply it as a wood vinegar or as a foliar spray. You can coat seeds. Of course, pH adjust the biochar first. And of course, there's other types of things you can do with it, such as a substrate and green roofs and walls. So all of that is gone over in the pros and cons in this chapter. And it also includes case studies, such as root zone application, mixing it with NPK, applying it with compost, coating seeds, green roofs, so on. We have a chapter specifically on case studies. I'm just going to emphasize one of them here. This is case one, feeding biochar to cattle for enhanced soil fertility and farm productivity. Feed the cattle. It's just 0.33 grams of biochar blended with molasses per cow per day. But you sow that comes out. That's aged in the animal gut, comes out. You sow your land with dung beetles. They take it down into the soil. You end up with a biochar way down deep in the soil, and the animals and the microbes did it all, and the bugs. So the results from that are improved feed efficiency, livestock health, and pasture quality. The net benefit was $12,000 per year, or $1,700 per ton of biochar, with a 12 times return on investment. Now, we summarize that in tables, and we end up producing a summary table of all the case studies. And we can't go into it, but there's the cattle biochar. Also, you can use biochar in feedlots and increase the weight gain on the cattle. You can use it in horticulture. We have a bunch of studies from Brazil where they applied biochar with cabbage, coffee, and maize. And we have a study from the US where biochar was used in golf courses. You work through all of that, the application rates and costs and so on, and you end up with a net benefit in the range very often far exceeding the cost of the biochar. And where it doesn't exceed it, such as with this cabbage trial here, it's still made a net benefit. You paid for your biochar, but this is based on just one yield of cabbage. You could grow another crop in the same year, and now you don't have any more biochar costs, so it's all benefit. And so you're suddenly back to your 100% return instead of a 2.3% return. So the net benefit can be quite large per ton of biochar. Just looking at the big scale study like a golf course, $300,000 to apply the biochar, but $2.7 million of revenue increase because of saved water and saved fertilizer. Net savings $22.4 million. You can finance that. And the finance cost is insignificant compared to these gains. So actually, you can do it with no investment and get a 10 times return. So chapter 10 is about biochar for regenerative agriculture. You're going to have to get the guide to find out everything in there, but this is just an illustration where biochar is applied in trenches along with minerals and compost, and promote the growth of fungi across your topsoil. You can, if you have solar panels, you can plant them so that the drip edge is over the trench, and the biochar collects and holds the water. You can sow your land with dung beetles, that's discussed before. So there's lots of ways of effectively integrating biochar and other nutrients and your creatures and other regenerative and energy producing facilities on the farm all together to great benefit and great profit. Now, chapter 11, I'm just winding up here, is how to test the biochar. We do advise you to test biochar in small trials and test the biochar before you apply it to soil. And we've got a chapter here where we show you how to test the primary constituents of the biochar, that is the amount of minerals and the amount of stable carbon and volatile carbon in the biochar. the soil relevant attributes like measuring the pH and the total dissolved solids, all important to get that balance right for your soil. And also how to do field testing to characterize your soils and the impact of biochar on the soils. So I'm going to wind up by just saying that's the guide. We are going to produce a manual, and the goal of the manual is to translate the massive base of scientific knowledge and some personal wisdom into profitable farmer practice. It forms the basis for training the practice and training the trainers of the practice. We want to engage farmers in furthering the practice and the science so the farmers can do small trials. It's really necessary to do that to optimize their return, and monitor the outcomes and report that back so that the science can be proven in the field and other farmers can see the benefit, and this can go viral basically. So yeah, think like a planet. I think we have to think not on our self-interest, but think like a planet, and that will be in our interest. Over to you, Paul.
Great. Thanks, Paul. Really, really interesting stuff. And thank you for going through it all. I'm sure everyone got a lot out of it. We'll go to our Q&A now. And there's been quite a lot of questions, and I know that that Melissa and Don, you've been answering some of them as well. So I might just start with one quickly. So how does that was asked in the chat. So how does the pyrolysis process differ depending on the feedstock and desired output, biochar, biofuels, etc.?
Great. We'll bring Stephen in to answer, give him a chance to address you too. Stephen, are you there?
Yeah. Okay. So the fundamental process of pyrolysis is the same. How you actually run your pyrolyzer is depends on a number of factors, feedstock being one of them. The biggest factor is the moisture content. There's an optimum moisture content between 15% is recommended, but you can run between 10 and 20%. So some feedstocks you have to dry. In fact, in some feedstocks, they're so dry that you actually need to add some water to them. There's by changing the temperature, you change the properties of the biochar. And Paul talked a little bit about that in his presentation. I think we encourage people, if they're just looking at crop yields and improving crops' resistance to disease, to run at low temperature. If you want to increase the water holding capacity or reduce if you've got a very clay soil, you might want to run at high temperature. If you want to get carbon credits in the voluntary market, they prefer you to run at high temperature. You get a higher carbon content and a lower hydrogen content. Carbon credits is an incredibly complex discussion. It depends who you ask for credits for, what they actually want. You want what sort of properties they want, but it's around how much carbon and how much hydrogen you have normally. So there's a whole range of factors that a manufacturer considers. I guess, you know, if you're on a farm and you want to do it very simply, then you can't really control the pyrolysis process. You get what you get. Yeah. You can have some control over it, but that requires a lot of skill. And one of the things when we run training workshops, we try to give people a feel for how different methods of controlling the rate of which you convert your biomass into biochar. So, you know, it's like many things, like farming. There's the science and there's the art. The more you do it, the better you get at doing it. it's unless you want to buy a very expensive pyrolysis machine that's been pre-programmed, and you just put the stuff in and the biochar comes out. And those modern machines are available. We've got 5 manufacturers in Australia of high-tech pyrolysis machines. But a lot of farmers want something that's simple and obviously something that's not capital intensive.
Yeah, great. And I suppose some of what you just touched on leads into the next question that was asked in the chat function was, how critical is temperature for pyrolysis? Do you need to reach a certain temperature to form biochar, or is it their amount of flexibility? So is there a certain sort of like degree Celsius that you need to get to, or is it really, I know you touched on saying that it depends on what you're after, but yeah.
It's unfortunately with pyrolysis, it's a time temperature relationship. So in other words, in fact, one of the first things I did when I got interested in all of this, I tried to make biochar in our home oven. It went to 250 degrees C, and I had to run for about 3 days.
Wow.
And after 3 days, I started getting biochar.
Yeah.
And I can't remember which figure it is, but if you look in what chapter is it, Paul? Is it chapter 3 or chapter 4? We've actually got a graph showing the range of which the time temperature curve that gives you a biochar. There's another factor in making biochar, is that the time temperature is also a function of the ratio of lignin to cellulose to hemicellulose. And it's also a function of the minerals that are in your biomass. Because some minerals actually help the pyrolysis process, they catalyze it, and some minerals actually impede it. So again, not a simple process. We've put a fair bit of information, but there's a lot more that we could have put in there in terms of what you've got to consider when you change your feedstock in terms of time and temperature to actually make consistent good biochar. I think the interesting thing is that if you look at traditional methods of making biochar, they develop procedures that were usually pits in the ground or very simple earth type kilns. They were, and some of the processes were very long-term pyrolysis processes. Some of them were very quick. And so one of the things that we do in our workshops is that I spend usually anywhere from a half an hour to an hour actually telling people what the different processes were that were developed all around the world. And there's quite a range, you know, from people that I visited in the hills in Nepal through to what we saw in Vietnam and the rice paddies, through to what they do in Africa. And especially the techniques that were developed by our own Indigenous people, especially around the Murray-Darling region.
Stephen, may I add something there? You know, in terms of making biochar on the farm, these indigenous practices, of course, the smoldering biomass are polluting, and we can get away from that and accomplish the same goal by using a flame cap kiln like the Contiki I showed you. Now, you don't have to worry about the temperature because you're setting the biomass on fire and you're burning a portion of it to process the rest of it. And it runs at a certain temperature. It runs at about 650, 70 degrees at the surface of the kiln underneath the flame. And then as the biochar gets covered, it's still heated, it still stays hot, and it's still processing and decomposing, but its temperature drops around to 450 degrees or so. And all you need is a heat to break down biomass. And you need at least 280 degrees typically, unless you want to go very slowly. But you're going to get 650 degrees, you're going to get 450 degrees. So what you're going to be doing is making biochars at different temperatures. And it's really hard to guess exactly what the plants and soils need. Yes, you can for specific constraints, but just you have all sorts of things going on your farm. And so it's really, in another way, quite simple. Now, when you make a biochar that way, it may not have all the properties and nutrients in it that you want and all the minerals that you want, but you can add those. You can understand the quality of the biochar you make in a contiki out of say a wood biomass, and then you can add the nutrients to it that you need to suit the soil and the plants.
Right. So yeah, so
Now, obviously, if you buy a commercial kiln, then they might be computer controlled and you can adjust the temperature that way. But don't be fearful that you have to have exactly the right temperature for your biochar. Probably a good thing if you have a range of temperatures, in fact. Okay, over to you, Paul.
thanks, great. And yeah, really interesting answer. So yeah, great to see that there is a bit of flexibility around that and that there's a lot to be learnt as well. So the next question was, in the Wollonga trial, was there a control without biochar to see SOC increase / change over the same time period? I'm not sure if you know that answer. Maybe Paul, you might know.
Sorry, I didn't get the question, or maybe if Stephen got it answered.
No, just repeat it again.
In the Wollonga trial, was there a control without biochar to see SOC increase and change over the same period?
Yeah. All of those trials. In fact, it's interesting because there was a woody biochar, a manure biochar, and a control.
Yeah.
And they kept on. And what was interesting is that the woody biochar, they got a response for a couple of years, but the manure biochar actually was still giving an increased response over the control after 10 years. And so one of the things that Paul pointed out is that high mineral ash biochars will give you a much greater response over a longer period of time than a woody biochar. And it's interesting, just to add to what Paul said, there's one of the techniques that Paul developed was with, say, a Contiki type kiln, you can actually produce a manure biochar at the most favorable temperature just by putting some manure in drums and putting it on top of the hot wood biochar. And I think Paul showed a picture of that. So
yeah, I did. And just we measured the temperature inside the drums, and it's even though it's in the flames at 650 degrees, the temperature in the drum is about 450 degrees. So you're making that nice low temperature biochar, and in fact, you're making both types of biochar. And frankly, they're both useful. The lower temperature biochars might be useful for certain chemical benefits, but the high temperature biochar might be really good for opening up your soil and water holding capacity and so on.
Right. Another question was, do you have a study on the use of a feed prescribed for reducing mortality rates?
Sorry, what?
Do you have a study on the use of biochar feed prescribed for reducing mortality rates?
Mortality of animals?
Biochar,
Yeah.
animal feed, yeah, for reducing mortality rates.
Yeah, look, I mean, charcoal versus biochar has been used by vets for we don't know how many centuries. Yeah. There's a few studies. There was a really nice paper written by Hans-Peter Schmidt on feeding biochar to animals. In Australia, I guess because the animal practices are really good, mostly what we've seen is improvement in weight gain, some improvements in milk yield. But the big thing about feeding biochar to animals, especially if they're in pastures, is the increase in pasture productivity.
Yeah.
But I don't think I'm just trying to think. Melissa, can you remember if there's any mortality studies? I can't remember.
Yeah, not that I know of, but I just wanted to comment on that from a feedlot perspective, because they push the protein very high, which can cause acidosis. And generally there's been comments from those using biochar in feedlots that there's less animal deaths, and sometimes those deaths are quite high. So I think there's merit in and doing a test on that, especially in feedlots.
Yeah.
I think certainly with running better animal health and better conception rates, and in a dairy study that I did, we actually found no mastitis when there was high cases.
Let me describe a couple of really notable animal or longevity mortality effects that come out of Japan and presented to us 15 years ago or so. One was with chickens. This farmer had chickens that were very, very unhealthy, and he started feeding them biochar, and the chickens got very healthy, laid super eggs, and he actually could charge a lot for those eggs, and he become very profitable. He was so impressed that he didn't mind his chickens getting sick, because he knew he could fix them and make them even healthier. The other example is out of Japan, was trees. I think they were pine, right, Stephen? But they were pretty sick, and they put biochar entrenched around the trees combined with effective microorganisms, and the trees come back to life and got really healthy. So whether it's plant or animal mortality or longevity or health, biochar anecdotally can be very, very helpful.
Yeah,
And with humans too, of course.
yeah. One of the
And we both use it. We both use biochar.
yeah, I take it every day. One of the other areas which has been really successful is using engineered biochars to go into on bedding, especially for chickens, but also for other animals. And it absorbs ammonia, it reduces pathogens. I'm just trying to think, there was I'd have to go back, it's too long ago, but they didn't look at mortality, they just looked at health and disease. Yeah, so there's quite a few studies looking at health and disease, but I can't remember anything that was done on mortality. But yeah, I'll go back and have a look. I mean, there's a lot of papers out there, and we just don't keep everything in our head anymore. I guess the one thing to emphasize that there's been a lot of work done mixing wood vinegar with biochar, because the wood vinegar is very good at suppressing disease. And I think there's about 4 manufacturers or 5 manufacturers of wood vinegar in Australia now, Don.
There is, yeah. Yes.
Yeah.
Yep.
And
so
I mean, I use it in my garden.
1%.
In fact, we're just I've got one of my collaborators and I have just actually done a review of 250 papers on wood vinegar, and we're about a week away from submitting that for peer review. But it was amazing the amount of new information that's come out in the last 5 years on wood vinegar. Very, very interesting results. I mean, we don't have time to talk about that, but potentially wood vinegar is going to have a big impact on pasture health and animal health.
Yeah, just to emphasize, when we talk about taking biochar or feeding it to animals or wood vinegar, you do have to be then more careful. But a biochar, it tends to be quite non-toxic, and the toxins aren't available from biochar. But nevertheless, there are requirements when you feed biochar to animals or wood vinegar, and the Japanese, for example, refine their wood vinegar quite a bit more carefully if it's for feeding to animals than for plants.
Right.
I was just going to add to that quickly, Paul. Doug Powell certainly noticed in their study that the fertility rate improved with feeding it to animals. So that might suggest that if it helps with life, it might help with mortality.
Yeah,
If they're getting healthier, you can be pretty sure mortality's going down.
yeah, great. Well, we've still got a few questions, but we've reached 1 o'clock, so we're unfortunately out of time. I've noted all of them down, and I will share them with you guys, and maybe we can get a written response, and we can share that online afterwards. But thank you everyone so much for coming along. I hope you've all learnt a lot, and maybe have a better understanding of biochar. And how the farmer guide that Ansbig has put together, and it's obviously a lot of work gone into it, and how that can be used and help your application of it if you're interested in doing it on your farm. And Don, the farmer guide's available on your website?
That's correct. Yes, you just go to ansbig.org Farmers Guide. It's on the top menu. There's also a QR code that we shared there. And just to quickly mention, we have got a Kickstarter crowdfund campaign, which includes and I put the link in the chat there, but that's to help support this work and to produce the next step-by-step instruction manual. So we're looking to raise about 300,000, and we're almost 80,000 at midway. So anyone who'd like to contribute is very welcome.
I just wanted to mention too, if anyone wanted to purchase biochar or technology that makes biochar, go to the ANZBIC website. All the members are starting to advertise their technology as well. But you can go there and you can contact myself or Don as well and put you on to the correct people.
Great. Well, everything's on the website, so we'll send out a link to that as well afterwards. The session was also recorded, so we'll be putting that up online later on. So thank you for all coming, and we hope to see you at another one of FCA's webinars or info sessions soon.
Just let me emphasize that the climate is it's a much more complicated thing. There's many more moving parts to it than we're really taking into account. It's absolutely crucial we cut emissions and draw down carbon. There's billions of tons of it have to be drawn down, and farmers are the best equipped people to do that, along with producing food and producing other regenerative benefits. We have to think like a planet, understand how the planet works, and get to work.
Great. Well, that sounds like a great point to end on. So, see you, everyone.
Thanks so much.
Bye.